In this lecture, we will be discussing electron configuration and how that's related to chemical nature or chemical reactivity, metallic behavior, the formation of ions and the definition of isoelectronic, and finally size of cations and anions. We've talked about the organization of the periodic table, and an important result of the way the periodic table is organized, because it's organized based on the alphabet principle or the filling up principle, is that elements that are in the same group or in the same column have the same electron configuration. So if you look at group 16, or sometimes this is called group 6A, all of these will have 2s2, will have a ns2 np4 electron configuration. So because of this, we have similar reactivity within the same group. Really striking examples are the group 1 metals and the group 7A. So the halogens all really have very similar reactivity, and group 1 metals have very similar reactivity. And this is shown here. All group 1 metals or alkali metals will react with water and displace hydrogen gas in a violent reaction. And all group 7 halogens, 7A, will react with metals to form ionic halides. So this is just an example of how having the same electron configuration gives rise to similar reactivity. Part of the reason for this is that elements want to go to a more stable electron configuration. Specifically, they favor this noble gas configuration. And we'll talk more about this later when we talk about the formation of ions. So there's 3 classes of elements: metals, so here we have a picture of carbon and sodium; nonmetals, neon, and this is liquid nitrogen; and metalloids. Silicon is a metalloid. So metallic behavior, metals are typically shiny solids with moderate to high melting points. They're good conductors of heat and electricity, such as copper wire. Copper is often used as the metal to do the electrical work in your home. And metals tend to lose electrons, and they are easily oxidized. And you're going to do an oxidation lab. Metals, because they have a low ionization energy, they can be oxidized easily, and they can have a sea of electrons to make them good conductors. Metals are often good reducing agents, and we'll talk more about oxidizing agent and reducing agents. Okay, nonmetals are typically not shiny. They have low melting points, and they tend to gain electrons and form anions, so they're easily reduced. Reduced means that they gain electrons. So nonmetals are typically good oxidizing agents, and again, we'll talk more about reducing agents and oxidizing agents. Okay, so I want to talk about ions. So atoms can either lose electrons and form cations, or they can gain electrons to form anions. So a cation is formed when an atom loses an electron, and anion is formed when an atom gains an electron. And atoms typically gain or lose electrons to achieve a full outer shell or a noble gas configuration. Lots of times elements will want to gain or lose electrons so that they have the same electron configuration as the noble gas. So we say that it's isoelectronic with a noble gas, meaning it has the same number of electrons as the noble gas. An example is sodium. It has an electron configuration of 1s2, 2s2, 2p6, 3s1. It will lose an electron to form 1s2, 2s2, 2p6. So now it's isoelectronic with neon. So sodium is a group 1 metal. So the group 1 metals, because they just have one extra electron from that noble gas configuration, will easily lose an electron. Bromine, on the other hand, is in the group 7, so it's just one electron away from having a noble gas configuration, so it will gain an electron so that it can become isoelectronic with krypton. So again, isoelectronic. Iso is Greek for same. So if 2 species are isoelectronic, it means that they have the same number of electrons. So this is an example of an isoelectronic series, S2 minus. So if sulfur gains 2 electrons, it's isoelectronic with argon. If chlorine gains 1 electron, Cl minus, it's isoelectronic with argon. Potassium will often lose 1 electron to form K+, which is isoelectronic with argon, and calcium 2+ will calcium will lose 2 electrons to become isoelectronic with argon. So all of these have the exact same 3s2, 3p6 electron configuration. And you can notice this really big difference in size, and we'll talk about this in just one second. This is, again, a figure from Silverberg, but this is just showing that group 1 and group 2, they're just two, they have a couple extra electrons, so they'll lose electrons to achieve this noble gas configuration. And groups 6a and 7a will gain electrons to form this noble gas configuration. So these are the ones that you can definitely predict. A lot of the elements that are in the middle of the periodic table are much more difficult to predict and depend on more factors besides just this full sublevel. Okay, so I wanted to briefly talk about the difference between ionic size and atomic size. So cations are smaller than their parent atoms, where anions are larger than their parent ions. So I wanted to go back to this picture to help you understand size. So all of these species have the same exact number of electrons. S2-, chloride, argon, potassium+, calcium 2+. They all have an electron configuration of neon, 3s2, 3p6. The difference is the number of protons. Sulfur has an atomic number of 16, chlorine is 17, argon's 18, potassium's 19, and calcium's 20. So calcium has 20 protons, whereas sulfur only has 16. So because calcium has so many more protons, it has a much higher effective nuclear charge, so it's going to pull this same electron configuration much tighter to the nucleus than our S2- does. So this is why our cations are often much smaller than our anions, because they have a much larger effective nuclear charge. This is another picture from Silverberg that I thought was really nice, just showing how the cations of different species are much smaller than their parent atoms, and how the anions are much larger than their parent atoms.